Welcome to the third video in our Class 23 series of lecture videos. We're going to continue with chemistry of alkenes, and in fact today we're going to talk about the hydroboration of alkenes. So boron is an element that's near and dear to my heart. I did a lot of my schooling in California, and in fact driving back from the San Francisco Bay Area to my home in Phoenix. During that time, I passed through a small town called Boron, California. In fact, my car broke down outside of it. I was just lucky enough to pull off the freeway and make it to a block or so away from the one store that functioned as a hardware store, video rental store, and a convenience supermarket. And they just happened to have the battery that I needed to replace in my car so it could limp on into Barstow, where it had its alternator replaced. Anyways, it was an interesting time for me to stop in Boron, California, since I did a lot of work with boron in my graduate degree. So with that story through, what is hydroboration? Well, it's the addition of a boron atom and a hydrogen atom to an alkene. And we say it's concerted. We have to remember that hydrogen is more electronegative than boron, so it's really functioning like a hydride. So it's not like a proton in a mineral acid addition. The boron is more like the proton because it's got the delta plus sort of characteristic. It has an empty p orbital, which accepts a couple of electrons. So really this is a Markovnikov addition. It's just confusing for us because we're used to seeing the hydrogen atom act as the electrophile, but in this case it's the boron. We get syn addition of that hydrogen and boron atom so that they add to the same face or same side of the face of the alkene. And in theory we could do 3 hydroborations. React 3 equivalents of alkene with each equivalent of BH3. And so we won't always end up with 3 alkyl groups on boron. There are some alkenes that would be too sterically hindered, but for most cases we do. So for example, how about an asymmetric alkene? Here we go. We've got this alkene which has a CH2 on one end and it's got this 6-membered ring on the other. And we do hydroboration, and lo and behold, the hydrogen goes to the more substituted carbon, and the electrophile, the boron, goes to the less substituted carbon. And we do this 2 more times. We form 3 boron-carbon bonds. Well, what good are boron-carbon bonds? Oxidation of them gives alcohols. Here we have triethylborane. If we oxidize that with hydrogen peroxide and sodium hydroxide, we get ethanol. So here we go. We'll oxidize this trialkyl borane that we formed in our example above with hydrogen peroxide and sodium hydroxide. And interestingly, we get this alcohol. So this alcohol, through the process of hydroboration and oxidation of this alkene, it looks like an AntiMarkovnikov product, like we added water across that double bond in an AntiMarkovnikov sense. Because if we had just put the alkene in acidic water, so if we had put this alkene in water with H2SO4, we would have added a proton to this carbon, and the OH would have been bonded to the tertiary carbon, which we consider Markovnikov addition. So the process of hydroboration and then oxidation gives us what looks like an AntiMarkovnikov product. However, what I can assure you is the hydroboration of this alkene is actually Markovnikov. The more electronegative hydrogen ends up at the more substituted carbon, and our electrophile, which is boron, ends up at the less substituted carbon, which is what the case would have been if we were protonating it. Our proton would have ended up at the less substituted carbon, making a carbocation out of that tertiary carbon, and the water would have added into that. So hydroboration really is Markovnikov. However, the process of hydroboration followed by oxidation gives what looks like an anti-Markovnikov addition of water across the alkene. It's a complicated idea. Definitely ask me a little bit more about it if it's something that is perplexing at class time. And we'll discuss a little bit more about it. In our next lecture video, we will show you what the mechanism is for this oxidation process. It's kind of interesting, but we'll wait until then.